Welcome to qnawire.
In this problem, we have two metal discs that are connected together, which have the same axis of rotation. Now, the now a block of 1.5 kg is attached to the smaller metal disc, and we can see that this green disc is the smaller one with radius r1 and mass m1, and the red arrow denotes the radius of the bigger disk, which is R2, mass is M2. Now, since there is torque involved or rotational dynamics involved, we'll be applying F sum over F equals MA on the block, since the block is free falling downwards and it's a linear motion. Also, we'll be applying tau z equals I times alpha z on the blocks because it's a rotational motion here. So this will be applied on the block and this will be applied on the combination of the metal discs. So together the combined moment of inertia is the moment of inertia of smaller disk plus the moment of inertia of the bigger disk. And we know that I for a metal disk is half mr squared, where m is the mass and r is the radius. So combining that here, we get the total moment of inertia as 2.25 times 10 to the power minus 3 kg meter squared. So let's look at this equation first, or the linear part. So for the linear equation, we can see that there is mg, which is acting downwards, and there is tension, which is acting upwards. And combining these two, we have an acceleration a in the downward direction. So we can write mg minus t, which is equal to ma. The reason we subtracted mg from t is because the box is going downwards. That means mg is greater than t. So this is the linear equation that we got from F equal to ma. Now for the torque part, we see that since there is no external other force involved than the tension, so T times R will give us the torque. So T times R will be equal to I times alpha, which is again another expression for torque, which we can write as A over R. Now the reason we set alpha equals to A over R is because there is rolling without slipping. So if there's rolling without slipping, then we can set A over R as alpha. Now if we solve for A from these two equations, we see that A will be equal to G times M over M plus I over r squared, where m is the mass of the block. So now we have to figure out the um, acceleration a when the string is wrapped around the edge of the smaller block, and we have to do the same thing with the larger one. So let's do the smaller one first. So for the smaller one, um, m is 1.5 kg for the block, but r is 2.5 times 10 to the power minus 2 meters. Using that in this equation, we see that A will be equal to 2.88 meter per second squared. Let me write down that equation here so that we know what we're doing. So A is G times M divided by M plus I over R squared. So what we're doing here is we're taking m as 1.5, g as 9.8, I as the one that we figured. So I is 2.25 times 10 to the power minus 3 kg meter squared, and r for the smaller disk is r1, or for the small disk is r1, which is 2.5 times 10 to the power minus 2 meters. Similarly, for part B, our m is again the same, but r now is r2, which is equal to 5 times 10 to the power minus 2 meters. And using that, we get A as 6.13 meter per second squared. Thank you.